In an introductory calculus class, they'll talk about two major ideas. One is the derivative, and the other is the integral. This is climb time, and in this video, we will answer the question, what is the derivative? So here we have a graph of an object being thrown up in the air, hits a peak and comes back down again. We usually refer to the y-axis as height, or sometimes s. S is the general variable that'll work for any position function. And then this is time. So it models the behavior of the ball as it goes up, hits a peak, and then comes back down again. And this represents the height over time. And this is the function for the equation s of t equals 64 minus 16 t minus 1 squared. And one thing we learned in a previous video is how to find average velocity. Average velocity is the rise over the run, and it would be the position at B minus position A over B minus A. So it's basically change in y values over change in x values. We call that the slope of the secant line. So if I draw a secant line, and if you're not familiar with the word secant, yeah, how good I am at doing this. Hey, that wasn't too bad, honestly. If you're not familiar with the term secant, secant means basically it intersects at two spots. So this line intersects at that spot and that spot. And so this spot over here, that would be at the peak of the throw, or the peak of the ball as it's going up in the air, is at t equals 1. And this represents where it hits the ground at t equals 3. So this would be the interval right here from 1 to 3. And we want to find the average velocity of that. And so that's not the actual velocity of the ball because the velocity of the ball keeps changing, but it's the average velocity from when it's at its peak to eventually when it hits the ground. All right, now I could do this again at 2.5 seconds. And if I draw another secant line at 2.5 seconds, how good I am at that. Not horrible, not horrible. And that's that would be the average velocity from t equals 1 to 2.5 seconds. Now let's think about this for a second. So I throw a ball up in the air, it goes up, it hits a peak height, and then it starts coming back down again. So its speed at the peak must be 0 because it has to slow down and stop before it can start speeding up again. So the speed at the top is 0. As it starts coming back down, the speed or velocity continues to get bigger in magnitude. The speed gets bigger. We would call that a negative velocity because it's going down. But it gets bigger in magnitude as it keeps going down until right before it hits the ground. So we'd expect our average velocity from the peak to there to be a higher magnitude than from the peak to here, which is 2.5 seconds. And then we could do the same thing at 2 seconds. Let me try to draw that again. Get the white one for that one. And see how good I am at that. Not too great there, but that's okay. And that's at, I'm sorry, that's at 2 seconds. So that would be at 2 seconds. And then we'll do one more at 1.5 seconds. All right. And then what you can see here is these secant lines are flattening out. Okay, it's getting flatter and flatter and flatter. And so what we're doing is we're trying to hone in on what the speed is at t equals 1. And by finding the speed at between 1 and 3 seconds, and 1 and 2.5 seconds, and 1 and 1.5 seconds. I'm sorry, 1 and 1.5 seconds. We're getting closer and closer and closer to the speed actually at 1. And we know at 1 it hits the peak. It's right at the top. So we know the speed at 1 is actually going to be 0. So we'd expect these speeds to get closer and closer and closer to 0. So let's see what the numbers come out to be. We learned how to do this in another video. So from 1 to 3, it comes out to be, I like the green one. I'm going to use the green one for this one. It's going to be negative 32 feet per second squared. And so from 1 to 2.5, as you can see, it's more flat. So we expect that number to get smaller in magnitude, which is negative 24 feet per second squared. Now I use the term magnitude. What that means, smaller in magnitude, means that it's getting closer to 0. Even though when a negative number gets closer to 0, it's technically getting bigger, but it's getting closer to 0, so it's getting smaller in magnitude. So its absolute value is reducing. So then from 1 to 2, it goes to negative 16 feet per second squared. So I worked out these calculations ahead of time. And then finally, at 1 to 1.5, it becomes -8 feet per second squared. So what's happening is the slope, this one right here, the first slope we looked at, that is -32. And the next one is -24. Next one's -16. The next one's -8. 8 could be improved a little bit there. So what you can see is it's getting flatter and flatter and flatter, closer and closer and closer to 0 as the magnitudes of these go down. So what would happen, I wonder, if I went from 1 to 1.001. So I'm very, 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 very close now to t equals 1. What would happen to this slope? What we would expect it, or the speed, the slope is a speed, we expect to get very, very close to 0. And in fact, it does. It comes out to be negative 0.1 feet per second squared. So you can see what happens here. You can see a pattern and you can see convergence. So as our interval starts to get smaller and smaller and smaller and smaller and smaller, our average speeds get closer and closer and closer to what we would call an instantaneous speed, which is a speed right at t equals 1. And what we'd expect is that instantaneous speed to be 0 because we know that's where it hits its peak. We know that's where it stops moving up and it starts moving down. So the speed should be 0 at the top. So you see this is getting closer and closer to a speed of 0. And if I continue to make this interval smaller, 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 we expect this number to get closer and closer and closer to 0. Okay, so these are secant lines. Now, this is true for any function. So for any function, we can say, it's not just for speeds, it works for any functions. For any function, we can say that the slope of the secant line, here I'm gonna try a new color now. The slope of the secant line, again, remember secant line means you have 2 points, is gonna be, the slope of the secant line is gonna be change in y. It's basically slope, so change in y over change in x. Okay, that's your slope. And that's going to equal f of b minus f of a over b minus a. Okay, that's the slope of the secant line because we have 2 points. So we can see that this is the slope of the secant line specifically for position function. And so that's specifically going to give us velocity. And this is the slope of any secant line, change in y over change in x. Now, how do we get from a secant to a tangent? So the way we get from a secant to a tangent is, tangent means it only hits at one spot, is that we need to get this interval closer and closer and closer together. We need to take these points and move them closer and closer and closer together until eventually they come together. So the way we're going to do that is we're going to identify this distance right here from here to here as h. All right, so that's h. And so that means while this is true here, we can also say that this is equal to f of a plus h minus f of a all over h. Okay, so f of a plus h minus f of a over h, because b is just going to be whatever a is plus h. And so the first time h was 2. The next time h was 1.5. And that would be from here to here. The next time h was 1, then it was 0.5, then h was 0. Actually, we never did h is 0. H is 0.001. So we can take b to be a plus a little bit more, however much more we want, minus the original f of a, so that's your rise, and then your run is h. So that's another way to write it. So now we have the slope of the secant line, which is the slope of 2 points. But what if we want those points to get closer and closer and closer together? Actually, it's going this way. Closer and closer and closer together. We want those points to get closer and closer and closer together. So instead of a secant line, we want those 2 points to come together and become 1 point. Well, we have a name for that. It's called the tangent line. So what if we wanted the slope of the tangent line? So here's the thing, is that the secant line approaches the tangent line as h approaches 0. So as h approaches 0, that means this distance from here to here gets smaller and smaller and smaller and smaller, which basically means the secant line, which is 2 points, becomes closer and closer and closer to 1 point, which is the tangent line. So here's the bottom line. Here's the takeaway. And that is what we want is the slope of the tangent line. Slope of the tangent line is going to be, and we learned about limits in a previous video, but it's going to be the limit as h approaches 0, because that's how we get the secant line to turn into a tangent line of our little formula for secant line. F of a plus h minus f of a all over h. And that is the takeaway. That is the derivative. So that is what all of this was setting us up for, is to learn what the derivative is. And so this is what we call the derivative. And that is what all the fuss is about. The derivative is the slope of the tangent line. And it's defined as the limit as h approaches 0 of f of a plus h minus f of a all over h. That's the slope of the tangent line at a specific point A. So this part right here gives us the tangent, and this part right here gives us slope, rise over run. And as these 2 points get closer and closer together, as the distance between A and B, which is h, the distance between A and B, h gets smaller and smaller and smaller and smaller, then the slope of the secant line becomes eventually the slope of a tangent line. And that's what derivative is. Get these secant lines to get closer, closer, and closer to a single point. And as they do, then you get the slope of the tangent line. Tangent is 1 point, secant is 2 points. So in the case of velocity, the slope of the tangent line is considered an instantaneous velocity. So there's a lot of great applications of the derivative, but this is what it is. The derivative is the slope of the tangent line. And here's its definition taken from a point A.